start talking about data and sound, and we'll talk about graphics later. But in particular, we'll sort of handle the sound, or at least part of it today. Okay, so you could put data into a basic program you have the data keyword at the beginning, and then a list of stuff. And then when you read from it, basically it's going to read in order from the first one, right? So for example here, if I do, let me just type this program in, 10 data 1, 10, 5, 20 data John, Paul, print, 30 read A, B, C, 40 print A, B, C, 50 read A $, B $, C $, 60 print A $, B $, C $, and then that's it. I don't even need to put the end in. So, okay, good. Let's run this. Okay, so let's look at what happened there. Okay, so how did it read all this stuff? Dang it. There, finally. Okay. So, yeah, how do we read all this stuff in? Well, in the order in which that I put everything in the data. So notice that I put, and I just, obviously made this stuff up, right? There's nothing special about these numbers or the strings. Is 1, 10, and 5. Well, when I read A, B, C, it's going to read them in order. So A became 1, B became 10, C became 5. And then on the second read command, well, now I've gone past the 1, 10, and 5. So the next three things that would be read in are John, Paul, and Prince. And so I obviously knew that those were strings because, well, that's obvious. And so that's why I did $signs for the second set. By the way, $sign and A are two different variables, even though they both have the letter A, right? So the data type and the name are relevant. But, I mean, in this case, it doesn't really matter, right? So I haven't done anything like where I've redefined the type of A. There's A and there's $, and those are different. Okay, anyway, so yeah, it loads them in the order that they're presented. And essentially what happens is every time you hit a read, there's basically like a pointer type thing that keeps track of, well, which one have you read? Okay, so if I read in A, but not B or C, then the pointer would be pointing to, okay, 10 would be the next thing that would get plopped into a variable the next time I hit a read instruction. Okay, you can, as I've done here, combine them so that I kind of essentially read A, B, C is assigning, that'd be like doing read A, then read B, then read C. But obviously this is a bit more expedient way of doing that, particularly if you want to do sort of multiple things at a time. And I went with demonstration involving 3 numbers here, simply because we'll use that exact thing later. It'll be 3 numbers at a time, not 7. I mean, you could do more or fewer, right? But I just picked 3 for the sake of demonstration. Yeah. Sure. Well, but it still have to have $signs because those data objects are strings. Okay. Yeah, because the data here, the first 3 pieces of data are numeric, but the second 3 are strings. No, there is also an integer type, but for the most part, you kind of want to avoid that. We'll actually look at an example where that gets used. But yeah, it's basically numbers or strings. That's it. Yeah, Drake. Yes, they're optional. Okay. And this is nice. Why did I put the quotes around print? Yeah, exactly, because it's a keyword, right? So I have to put quotes around something that's already part of the language for the sake of the data. John, does that not jive with something? Or do you realize that's going to really screw you over yet again?
Well, no, that's fine.
Uh-huh.
Does it work with the mark?
Um,
Because for mark, if you do like a line and you just throw CH or dollar sign at the front, then you can count it up as a single quote at the front of the row.
oh, actually, yeah, for the purpose of tokenizing, you could just ignore the line. The only thing I don't remember if data has a token attached to it. It does? Okay. But everything after it, you just leave alone. Yeah. So, um, yeah, which is handy, right? Okay. So anyway, yeah, and the data here doesn't have to be at the beginning, although that's certainly a logical place to put it. Um, I could have put those two data lines at line like 70, 80, or so on, and it would have worked. Okay. Well, let's just demonstrate it. Okay, so let's create a new, right? So then let's do 10 read A, 20 data 5, 30 print A, right? And in fact, I could actually do it this way. Let me add 40 read B, 50 print B, 60 data 7, right? So the interpreter, it doesn't have to be in order. The interpreter will go out and find data lines, even if they're not at the beginning. So that's kind of handy because it means that you could do, for example, your program with 10, 20, 30, 40, and so on, but then put all your data starting at like 1,000 or something. Okay. It doesn't have to be in any particular order. Now, doing it all at the beginning or all at the end is certainly a logical approach just for your own sanity. But as we're going to see, if you've got lots of data, doing it at the beginning is maybe a bad move. Okay. So we'll see that in just a second. Okay. So kind of make sense? Yeah. And like I said, there's nothing special about doing 3 of these per reader or whatever. But the next example we'll look at has that, and so that's why I just picked 3. Okay, good. Now, of course, we could also store this stuff in a separate file and use some like get or input with open and file access kind of stuff. The data thing is if you're storing it within the program itself. So it'd be the program contains both its code and its data rather than relying on a separate file. Okay, so that okay? Yeah. So let's see. I want to go to here. Okay. So we could do some of this stuff with other files. Get an input right are going to pull in either characters or strings, and if it's a string and you do some processing appropriately to like let's say you had a list of numbers, you'd want to pull in basically and then start to carve up every time you hit a comma or something, right? It'd be obviously a little bit more complicated, but we certainly could do that. Okay, so let's talk about sound, and in particular how the C64 is able to handle sound data. Okay, so there's a chip in there called the SID chip for sound interface device or something like that. And it's a separate chip that's on the motherboard of the thing, separate from the processor, separate from the video chip, and so on. Okay. Um, it is capable of producing 3 voices at a time from a sort of small selection of different waveform types. So sawtooth, square wave, sort of sine wave kind of thing. And so it's going to be super synthy sounds, and it can have 3 of them going at a time. Okay, which seems like a kind of limiting, doesn't it, Rippy? At a time. Hmm? Yeah. So sorry.
What kind of range in the waveform?
Oh, like in terms of their frequencies?
Anything?
Well, I mean, within human audible.
Okay, so
Yeah.
with like all the different like
Yeah. I mean, within sort of, it can do basically 8 octaves worth of notes.
so you only did 3 watts.
Right. Sorry. Them's the breaks. And actually, this is something I just learned a couple days ago, and I was reading about this. The guy who designed the SID chip uh, at MOS, he ended up leaving and founding Ensoniq, which is a synthesizer company. And basically, the first Ensoniq, the chip he developed for that, was what he wished the SID could have been. So he was really under the gun to get the design done. And so that actually explains some of the limitations of the SID because he just, he didn't have as much time to do it as he wanted to.
Do you have any examples of things that were waiting on Calgon?
In a moment, yes. Okay. It's almost as if the professor has kind of thought out the structure of the course. Right. And yeah, so we'll look at an example here in a moment. And one of the things that we'll need to do is you'll specify frequency, volume, duration. And then also, you don't have to do this, but you have the ability to use what's called attack, decay, sustain, and release. Okay. So the wave, or the sort of what those 3 things are, is attack is sort of the initial part of the sound that can get louder than the decay, which decays down to a particular level that you sustain and then you release it. Now, you don't have to use all 4 of these things every time, but that's what allows you to get fading tones or kind of some complexity to the sound. Okay. Yeah, Rippy has an evil grin under his mask, no doubt. Okay. Okay. So let's look at an example. And for this example, this is coming from page 185 of the Programmer's Reference Manual, which I'll put up here on the screen. And then also, so I posted both of these things to Canvas. And let me get the. All right, so we've got, let's see, which one do I want? Programmer's Reference Manual. Here it is. Okay, so I want to put this on the right half. Okay, and then let's go down to page 185. Okay. Okay, so here's the example we're going to look at, which is a little hard to read here, perhaps, but that's okay. I'm going to load this. So the other thing I put on Canvas is there's somebody at some point basically typed in all the programs that are in the manual and made a D64 of it that is freely available. Okay. So that thing basically has all of the programs that are in the examples in the reference manual pre-typed in, which is huge. Okay, so let me attach that disk image and okay, so it's got a bunch of programs basically all tied to each page, okay, of the manual. Okay, so I want to look at, and let me close this, get it out of the way. I want to look at the example here on page 185. So I'm going to load that program in. Oops, it would help if I was in the correct window. Okay, now let's list the program. Okay, so this one's not super long. It'll fit on a screen. But in particular, there's a crap ton of data down at the bottom. Okay, and notice that they basically are organized into groups of, in this case, 6s, but the way I want to think of that is in groups of 3 because of how they're going to get used. Okay, and So what this thing is going to do is it's going to read 3 at a time from the data pool, and it's going to put those values out into certain memory addresses. Okay. Now, the base memory address here that we're going to use is 54,272 decimal. Okay. This corresponds basically to the base address of where the SID chip's registers are located. Okay. So the SID chip has internally a bunch of registers. How does the processor communicate with those registers? They're all memory mapped. Okay. So if you write to a particular memory address, most of those are going out to RAM. But some of them are sort of redirected over to the particular chips that are assigned to those things. The SID chip, for example. Okay. So the different addresses that I'm going to write to here are, and we'll look at what all those registers are, right? So S, notice that we've got S plus, um, let's see, we're going to poke values between that number and that number plus 24, okay, with all zeros. And what that's going to do is basically all 24 of the registers, we're going to write a 0 to them, and that's going to basically clear and sort of reset all the sounds. Okay, that'd be kind of like visually clearing the screen or something like that. Okay, good. And then line 20 is going to poke 9 and 0 to certain addresses and poke 15 to another address, and that's basically going to set all the volume controls. Okay, and then the main part of the program is what we'll look at next. Okay, so those first two lines are only going to run at the beginning of the program; they're not looped through, but it'll produce it'll basically just get things ready. Okay, good. All right, ready? Okay, so the way that the frequencies are stored, um, you need more than 2 bytes, or sorry, more than a single byte to store the frequency that you want to encode. Okay, and so the way that you do this is kind of like the pointers where you store a low byte and a high byte. Uh, we have to do that with the sound. So high frequency and low frequency is maybe a bad way to put it, but it's really the high byte of the frequency and the low byte of the frequency. Okay. Um, and for whatever reason, um, the person who programmed this um, put it high low rather than low high, but it doesn't really matter as long as you write the correct data to the correct byte. Okay, so looking at the poke statements here, where do we put the low frequency? It goes to memory address S, whereas the high frequency goes to S plus 1. Okay, that makes sense. Low, then high. That's the same order that we've done it in. But for some reason, notice which order he reads them in, high, low. Okay, so they're listed here in high, low, not low, high, whatever. Okay, we will need to make a convention on this for one of the assignments because we're all going to be doing pieces of it and then assembling the result at the end. And so let's go with the convention of low, high, always for our data statements. Okay, and that way we won't all have to retranslate each other's stuff. Okay, is that okay? Because low, high is more logical, I think. Okay. Okay, so what it's going to do is it's going to read in the high frequency, the low frequency, and the duration, okay, from this list of data. And so it's basically reading 3 at a time through this. It's going to put the high frequency in its register, the low frequency in that register, and the duration in the, or sorry, not the duration. Then it's also going to put 33 in this other register, and we'll look at what that is in a second. Yeah, Cole. Sorry, S is this number, right? That's the base address. So there's 24 registers in the SID chip, starting at address 54272, or whatever that is in hex. Right. So those memory addresses. So S obviously is 54272. S plus 1 is 1 past that, and so on. Right. So that little block of 24 memory addresses is actually the registers in the SID chip, not memory addresses. They're not truly memory addresses. Okay. But this is how we can, by writing to those memory addresses, the processor sends data out onto the address bus and the data bus. And the memory management thing is basically going to redirect it. Anything within these values actually goes over to the SID chip, okay, rather than to like a section of RAM, okay. Right, for the audio part. Now, the VIC chip that handles graphics also has a range of memory for its registers and its memory and so on, right? And we'll look at the graphic stuff later. Okay, good? Okay, so then the duration is handled basically, this is really silly in some sense. Look at how the duration is used. Look at line 80, DR for duration. It's a loop that does nothing.
Is there really not a wait?
Not in BASIC anyway. There are ways to do timer-based stuff using two of the chips. The complex interface adapters both have a timer circuit, two timer circuits, which will, but for that I think we'll talk about more in machine language when we get there. 80 Rippy, it's the 80s, right? This was announced in 1982, so this stuff was being developed in earlier in the like 80, 81, right? I mean, this was cutting edge though at the time. I know it's kind of scary to think that this was cutting edge, right? Mm-hmm. Okay, nothing. It basically is just a delay, right? So if I have a 4t equals 1 to duration, then the duration number, I'm basically just going to iterate through a loop that has no contents however many times, and that's going to slow down the execution of the thing until I get to the next, until that loop finishes and I do, the next node. Well, because I guess there's not really a whole lot better way to do it.
It looks so weird they don't put a space after it.
Yes, okay, because you don't have to.
Well, yeah, but like,
I know, it makes it hard to read, right? But yeah, okay. So let me actually change the audio output here to the projector because you guys won't be able to hear this. Okay, so sound preferences. I still want the sound input to come from my AirPods, but I want the output to go to the HD60. Okay, let me run it. And okay, let me crank the volume here. Hopefully you guys will actually be able to hear this. There's a reason for that, which is not hugely important. Right? Yeah. So the syntax error is because it's actually read, was it what line 190? It's these negatives, which basically, yeah, the program, it actually was breaking on negatives, but yeah, don't worry about that. Okay. Just don't worry about that. Okay. Yeah. Okay. So looking at the data lines here, then what do we have? We've got whoever wrote this, right? High byte, low byte, or high frequency, low frequency. I would have put them in the other order, but whatever. Okay. And look at our durations here: 250, 125, 750. There's a couple that are 63.
So it's high frequency, low frequency duration.
Yeah.
Then what?
High frequency, low frequency duration for the next note.
Okay. So it's the current note, next note, current note, next note.
Right. I mean, we could have doubled the number of data lines here and only had 3 on each line, but that would have made you could. Well, okay, you can't put it all on one because each line can be no more than, I think, what, 80 characters? Yeah. Right. It's just trying to organize it better. Okay. Yeah. Okay. So, wow, not particularly interesting sound, right? Because it's deets and doots basically. But hey, it works, right? And I just realized that there's no audio capturing going on with the with this on Twitch. So anyway, you won't be able to hear the. I'll have to change something about how I've got OBS working. Okay. Anyway, that's all it does, right? But let's sort of look line by line, okay, and think about the function. And in fact, in the reference manual, it gives us basically. So let me relist here so we can see everything at once. Okay, it gives us a line by line explanation for all of the well, the whole program. Okay, so the volume is set at line 30 to maximum. Okay, the attack and decay and the sustain and release are handled by addresses 5 and 6, or I guess +5 and +6. Okay, and that basically is going to control how the sound sounds, right? So if I change these numbers to different things, then I can change sort of the quality of the sound. And for some of that, you just have to kind of poke around, pun intended here, poke around and just kind of see how it works. Okay. Okay. If there's a high frequency less than 0, the song's over. So that's where it ends. That's basically what's generating our error, but it's not really a huge deal. And so it's essentially going to go note by note. Read the high frequency, low frequency duration, poke the high and low frequency to voice 1. Line 70 is gate the sawtooth waveform. Okay, we'll talk about that later. 80 is just sort of our timing loop. Release, okay, so line 90 is going to basically release the note and then go back and start it all over. Go to the next note. Okay, and then we've got all of our data. Okay. Okay, so does that make sense? Kind of, yeah. Now, obviously, what's sort of limiting about this example?
Would it be smarter to store the song on, say, a seek file and then read it in?
You could also do that. Right.
Then you could like give it a couple of the high frequency, low frequency, and then the duration. And you get like a whole wide list of like the entirety of the song in a seek file and just read that in.
Yeah, that for something bigger and longer, that would be much more logical, is to have the stuff in a separate file.
And then considering in the future of what we may have to do,
right.
That might be the best case.
Yeah. Yes, obviously that's a better way to go. Okay, so in particular, this is here's how the frequencies are encoded actually, and there's a table. We'll look at the table later using this this arithmetic. Okay, and the frequency that you want to create is not necessarily what you encode. There's this relationship to it, and we'll look at the table that basically just shows you, okay? The other thing, though, is we were only using voice 1 for this program, right? We could have also used voices 2 and 3 and had 3 notes playing at the same time. So let's look at an example where that happens, okay? Because if we want to make some real music here, right? Now, this one, right, yes, okay. So let's look at this one, right? Okay, so this starts on page 187. Oops, dang it. Right. Okay, let's run it. Womp womp. Okay, so I knew this was going to happen because I've ran into this before. Let's look at line 150, and let's look at line 150 in the book. Yeah, what's the problem? Yeah, there's a typo. Okay, so let's fix that line, and then it'll work. Oops. Yeah, dr percent equals, right? So 150 should be dr percent equals nm divide 128 colon OC percent equals nm minus 128 times dr percent divide 16. All right, did I get it correct? dr percent equals nm divided by 128 colon OC percent equals parentheses nm minus 128 times dr percent divide 16. Okay, got it. Oh, it's coming back out here. Sorry. Let me change that and we can.
So it probably sounded really cool to you, but no.
Oh, it sounds great to me. Okay, I'll rerun it because I want you to get the whole experience. 3 notes. That's it. Yeah, let me make sure it's not going to go back to my ears because I really want you guys to hear this. Well, no, that's actually normal. Okay, it is outputting to that. There's a delay before it starts because it's processing. Isn't that awesome? Yeah? Okay, so guess what our project is going to be? How to do this? Well, we'll go through, like, we need to dig through the code, right, to understand what's happening. Okay, this one's obviously significantly more complicated than the last one. Okay, but pretty cool, right? So, so your dear professor, who loves you and wants to, right? So what are we going to do? It begins.
Oh my god. It begins. Oh my god.
Well, I had to pick something. Well, okay. Okay, and we're, for the sake of our sanity, we're going to skip all that, right? So here's the sheet music for dear old Wabash. Okay. I'm not going to accept a Taylor Swift song because the assignment is old Wabash, and I'm not going to accept your crappy selections in music, Rippy. Okay. Okay, because if, especially, you know, if he's going to do Taylor Swift, then there's probably some other jerk in here who's going to either do the Rickroll song, okay, or you know, Nickelback or something, right? Okay. No. All right. So we're going to do old Wabash. Okay. And in particular, though, looking at old Wabash, okay, I just did realize something that may cause some complication. Well, there's that. Okay. But also that I forgot it's in 6/8 time, not 4/4. No, it doesn't have to be 4/4, but we'll have to. Some numbers may have to change. So I'll have to do some math. That's okay. Okay. Yes. Okay. So now, for how many of you is this in Greek? Yeah. You don't know how to read sheet music. Okay. That's okay. Okay. Well, do you see a key signature at the beginning? Well, then what key is it in? Thank you. Right. And here I am being all judgmental, right? Okay. Yes. Yeah. Okay. So yes. So what is this here? The top treble clef is the vocals. Okay. And the bottom two are the piano. Okay, that would be accompanying it. Right, so that's what's here at the bottom. Da 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 from the right, and so on. Okay, so or well, da 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 da, and then pause from the hills of Maine to the right. Okay, so we're going to sort of split this up a little bit in terms of because what do we have to do? We need to translate this into a sequence of numbers that we can use to actually play this song. You're not going to do the entire thing. Right. I'm going to assign you guys sections, so we're going to parallelize this process. Yes, but what I'm saying is that you're splitting it up into 1, 2, 3. Mm-hmm. You have the vocals and the harmony. Yeah, so here's how we're going to split this up. 3 of you are going to do the vocal. 3 of you are going to do the treble on the piano, and 3 of you are going to do the bass on the piano. There are also 3 pages worth of sheet music. So one of you will do 1 page, the other the other, right? So that'll split it up a little bit. Okay. Yeah. I mean, because translating this into those numbers right now, you have a giant problem. Yeah.
There's got to be like some way to figure out what the Commodore programs for each of them.
Well, okay. So we'll get to that in a moment. Oh, okay. So that's different than what I thought you were going to say, which was basically feed in the program the sheet music and out comes the Commodore data. Yeah. Okay. But that's what you guys are going to have to do, right? Is read this music and translate it to the appropriate things. Okay. Now, let's stop and pause for a moment, because what information do we need in order for the song to work? Well, okay, forget that. Each note needs what? Every single note needs three things: a duration and a frequency, and the frequency is split into two pieces. Okay, so we need to basically, looking at this sheet music, remember, or in some of your cases, learn how to read what notes are here. Okay, so now it's time for your music lesson. Yay? Okay, so what are these two symbols here? Okay, these are called clefs. There's actually more than those true, but we have treble clef and we have bass clef. Okay, and that indicates which positions on the staff are assigned to which notes. Okay, so right, so you have to remember these, right? So what on this one? Do you remember, Evan? This very first note is what? Uh-huh. Two down, C. Okay, so this is C. D, this next note is a D. This is an E, F. Okay, so another way to think of it is we've got the four blanks, F, A, C, E, face, right? Right. Okay. Okay. We've got two other things here, which is okay, so now the bass clef is different. Okay, so the same position on the bass clef is not the same note as it is on the treble clef. Okay, it's a different clef. Okay, so we'll have to look up basically for that one which lines or which spots correspond to which note. Okay. All right. Now, what else do we have on all these notes? Sharps, and in this case, there might be some flats later. Okay, so what are sharps? So let's take a look at these two notes, right? The hashtag that appears before a note, okay, yeah, it indicates it's up by half a frequency. So this note and this note are different, okay, by half of a frequency or half of a frequency interval, okay? Um, Okay, now don't worry, there is a table in the manual, okay, that basically says, okay, if this is a C4 or whatever, then which note that corresponds to and which frequencies. Okay, so we don't have to pick that out of thin air. Okay, similarly, there's the duration aspect here. We'll talk about that in a moment. Okay, um, okay, so we also have in this, there's a third set of symbols, and those of you who have seen sheet music before, shut up, okay? What do you think this is? It's a rest, okay? Which basically means that that note is not playing, or that voice is not playing for that unit of time, okay? Now, this music is divided into measures, okay? So each vertical bar denotes a measure. And how many beats are there per measure? There are 6 of them, and they are of eighth note duration, okay? So this is this is the time signature 6/8, okay? Which, fine, doesn't have to be in any particular thing. Most music, or a lot of music that you hear, is in 4/4 time. So each measure 1, 2, 3, 4. next measure, 1, 2, 3, 4, right? Not all of them are, okay, but certainly many are. Okay, this one's in 6/8. Great, whatever. Yes.
What about the ties?
The where?
Maybe you have like a story.
Yes, that like these. Okay, that's not something we're going to be able to do, but that's basically, yeah, the tying is,
Is it a no smoothing in the frequency?
I don't think you can do, well, I'm not sure.
Like he's on the far left of the floor, so you need
Yeah, okay, so like what they're asking about is here where the cotton, right, so how does it go? From the hills of Maine to the western plain, or where the cotton, right? So what's the difference between cotton, right? So what did I do there? I changed the frequency, but I was still, as opposed to cotton, right? We're making them two discrete units. Okay, we'll have to figure out a good way to handle that.
Is there a smoothing?
I'm not sure.
Okay.
Okay, so we'll have to figure that out. For the moment, let's just assume that there isn't and treat them as discrete notes. That's the easiest thing to do. Okay. Okay, now we also have another problem, and the piano immediately in measure 3 presents this problem to us. What is the problem? In measure 3 of the piano. Well, in terms of programming this.
I mean, there's still 3 notes.
We got 5 notes being played at the same time. How many notes can we play at the same time? 3. Okay. Now on a piano you can do this because of course you have 10 fingers and each note is a separate string inside the piano, right? And so you can hit all of them, right? In fact, I actually saw, this was floating around on Facebook, where it was the indications to the pianist were to flip around and place both buttocks on top of the notes from this range to this range and sort of hop up and down. Like it actually said this. It's kind of ridiculous, but yeah. So, okay. But point being, we can only play 3 notes at a time. Okay. So if we encounter a situation where a particular voice is indicated here that it needs to have more than 1 note, we have 2 choices for how we can do this. What's the easiest choice?
Always do the top 2 notes.
Or just pick one of them, right? Okay, so for each voice, bass and treble for the piano, just pick one of the notes. Okay, now you could always pick the high one, or always pick the low one, or always pick the middle one. Or if you've got a little bit of musical training, you could maybe decide which one is the most important. Okay, which might require kind of playing things out on a piano to sort of decide. Okay, but we have to make a choice. Okay, what's the other method of doing this? If we can't play them all at the same time, we could play them in rapid succession. That's called arpeggiating. Okay, so I'll give you an example where I use this in my own musical background. So how many of you guys knew that I used to play violin? Really? Just you two? Okay. So yes, I used to play violin. And one of the songs that I was learning to play, right. So 3. Yeah, no, the problem that you're going to have is like here, right? So where we've got the, here, right? We've got 1 note for the voice, 2 notes for the piano treble, and 2 notes for the bass piano, right? You can only play 3 notes at a time. So the voice can only do 1 at a time. The piano treble will only do 1 at a time, and the piano bass can only do 1 at a time. Right? So of these 2 notes, we have to choose which of those 2 bass notes we're going to play. Oh, okay. Okay. No. Because so you guys are all going to encode a separate piece, but then we're going to assemble all of it together so that we have the entirety of the song for Old Wabash that can play. Okay. That's the goal here, right? And the fact that there's more enough of you that we can subdivide this will mean that it's not as much work for any individual. But we're going to have to decide on some conventions so that we can take our collective pieces and put them together at the end. Okay, so does that make sense? The problem here? Yeah. Okay. So now the other problem. So arpeggiating. Let me give you a sense of what I mean by that. So let me go to. I think it's this one. I'll know it the second I hear it. Okay, let's go through the ad. Yep, that's it. This is probably one of the hardest things I've ever done in my life, was learn this. My fingers are even still like, it was just, and that was, goodness, guys, 20 years ago I was learning this. More than that. 25. This next part is one of my favorites in the whole piece. And not quite this part, a little later. This part. So you see how her bow's sort of seesawing back and forth, okay, quite a bit. And I mean, not just going back and forth, but sort of seesawing in terms of the angle. So the reason that that's happening, okay, is because how many strings can you bow simultaneously on a violin or viola or cello or bass? It's two. Okay, there are four strings, but you can only bow two of them at a time. And the reason is, so you see this part right here is called the bridge. Okay, you see how it's angled or it's curved? And so like only two strings are ever in line collinear with each other, and the bow can only therefore touch two of them. So when she's doing that seesaw motion, what she was doing was playing three notes at a time, but by doing rapid succession, right? And that part that I indicated a minute ago, where she was playing the same bass D note Right. So that's called arpeggiating when you do this. And it's the only way that you can play more than two notes simultaneously is with some kind of trick like that. So anyway, I'll stop that. You guys can listen to the rest later. It's beautiful. But now, so some of that, and this is me going to go off on my musical tangent for a moment. That part with the same root note the whole time, what you should be thinking when you hear that is an organ fugue. Okay, because if I were to play something on an organ, how many notes do I get at a time?
I mean, technically more than
12.
You only play 12?
You got 10 fingers and 2 feet.
I mean, but you can technically play it.
Maybe a little bit more. You could probably, if you're really good with your feet, you could probably hit more than one note at a time, right? Well, that works too, right? Play a duet. Okay. So yes, and quite common in this sort of Baroque era music, you have sort of bass root tone, often going to be your foot, that just plays and everything and sort of anchors everything else that's going on with your hands, right? So that was what was going on in that part, and the seesaw motion was because she needed to hit the D string to get that root D, but then hit the A and the E strings with whatever to hit those two notes, and then had to do this. I mean, like I said, this is a technically quite sophisticated piece. It was, because of that kind of thing you had to do. And when I was a teenager, I was minorly obsessed, pun intended, with Bach organ fugues. I went through a phase, right? Anyway, so, okay. So basically we have to make decisions, right, in terms of what to do for situations that have multiple notes. We can kind of arpeggiate it, or we can just pick one, okay? Now, my recommendation is that we choose the same thing because we're parallelizing this, and that is to say, let's all just pick one and not try and arpeggiate it, okay? We could always doctor that up later. Okay, now, in terms of which one to pick, that's kind of that's going to be musical taste here, right? Probably the best thing to do would be to choose the low note, okay? But I'm not sure. Let's just run with that and see how it turns out, okay? Does that make sense? Okay, so what, oh, and there's some flats, by the way. This is a symbol for a flat, so it looks like a B. Okay, so the flats and the sharps, so the octave is divided into, what does the word oct mean, or that root? So the octave is divided into 12 pieces because oct means, okay, now there's a reason for that, Cole, that's going to drive you crazy. If you play only the white notes on a piano, okay, then there are 8 of them per octave, hence the name, okay? Huh? Right. What? Yeah. So in the original, like in Greek music, you only had 8 notes per octave. Later, more got added. Okay. Now, in terms of the frequencies, the way this works is, so if I hit an A, any note on the keyboard, let me just pick A. Let me pick concert A, which is 440 hertz. Okay. That's the third highest string on a violin. And the concert master's job, by the way, is to play that, and everybody else tunes their instruments accordingly. Okay. Anyway, so 440 hertz. If I go 1 octave up from that A, what frequency is it? One octave up, what happens to the frequency? It doubles. Okay, so the next A would be 880 hertz. And if I went down an octave, it goes in half, be 220 hertz. Okay, so within that range of, say, 440 to 880 hertz, okay, which is the frequency, right? Each note, the white and black keys, are a division of 12 okay, within that range. Okay, but here's the problem. The division between each octave is not the same. Okay, so it's not divided evenly geometrically. Okay, or sorry, evenly like in terms of a linear thing. It's divided sort of multiplicatively. Okay, which is just beautiful. Okay, and so each note basically is the cube root of 2, or sorry, cube root of 12th root of 2 times the previous frequency. Okay, so that if you multiply by 12th roots of 2, what happens? You get 2, which doubles it. Okay, so 440 hertz is A. 12th roots of 2. Yes, okay. So the frequency, like how you go from one frequency to the next, okay, so let's take the concert A, 440 hertz. Okay, A sharp, which is the next note, right, is what frequency? It'd be the cube root of 12, or sorry, damn it, I keep saying this wrong. The 12th root of 2 times 440. 12th root of 2 times 440. What is that? Well, you don't just compute 12th roots off your top of your head? Uh-huh. Yeah, so let's do square root of 12 or 2, 12. Well, here, we'll just, right, 440 times 2 to the 1/12th power. Okay, and let me put a decimal. Yeah, okay. So the frequency of that the note that's 1/2 step higher, okay, that 12th interval, is 466.164. Okay. Yes. Just that note. What do we need? Okay, because we're not going to program in the number 466.124. Okay, or 164. We need to translate from the actual frequency in hertz to how it's going to get encoded. Okay, so great question. So let's look at how we do that. Okay, and for that, I was going to get to that eventually. Yeah, exactly. Okay, and write down. Okay, so let's go back to the manual, right? Okay, so Appendix E gives the frequency values you need to reproduce a full 8 octaves of musical notes. Okay. The other thing we have to talk about is the duration, and we'll get back to that. Okay. And basically, here's what. Let's talk about the durations. This is right here. Okay. Looking at these things, what are our durations for each of these notes? So let's go back up to the top and just take it. Okay. What durations do we see? So this note is a what? It's a quarter note, which means 2/8. Okay. And so this one is an 8th note. Okay. So this one has half of the duration of that one. Okay. Then what do we have here? 8th rest, quarter rest. Okay. And you just memorize these symbols when you learn to read music. Okay. So if we start with this measure from the hills of Maine to the, right? Okay, so you see, obviously the durations are different. So what are the durations here? We have a quarter, which is 2/8, 1/8, 2/8. How many eighths am I up to total? 5. And how much does each measure have to have? Exactly 6, because the time signature is 6/8. Okay. Okay, so if I only have 1/8 left of time, but I want to play 2 notes, what do they have to be? They have to be shorter than 8, or 1/16. Okay, so what the durations are based on the decorations. So no flag is a quarter, 1 flag is a 8th, 2 flags, and it's a little hard to see on the screen here, is a 16th note. Okay? This one? This measure? Okay, so quarter rest, so that's 2/8, 3/8. Yeah, that's a symbol for a quarter rest. Quarter rest, eighth rest, 3/8. Quarter note, 5/8. Eighth note, 6/8. Complete.
So, okay, so what's the sum of black bar between them?
In terms of, so those are eighth notes that are kind of, they're combined that way. So if you've got more than like a bunch of them in a row, rather than have lots of flags there, you put a bar, okay? And so obviously there's 6 of them, so they all have to be eighth notes. If there is a second bar, those are 16th notes, right? So what we'd have is eighth, rest, eighth, eighth, rest. That only leaves 1/8 left, bop, bop, 2/16. Huh? Yeah, okay, good. But there's more. What's that? Yes, okay. So there are also dotted notes that are 1.5 times what's otherwise indicated, okay? So if we do the math on this measure, we have eighth, rest, rest. This is a quarter plus an eighth, okay? So the dot basically gives it 1.5, multiplies it by 1.5. So this note is actually 3/8 in duration, not 2/8, okay? When it has a dot next to it, okay? Okay, so is that all right? And I don't think there's anything beyond those. Let's maybe look on the bass. Okay, so we've got some dotted stuff. I don't think there's any half notes in here. Oh, yep, there are, of course. Okay, so the ones that have no flag and aren't filled in are half notes. But this is a dotted half note. So it's 6/8, which is the entire measure. Okay, so that note would be played for the entirety of that measure and then be released at the end of that measure. Okay, now obviously in this case though, we got a problem, right? Because we can't do all of this. No, so we can only pick one note or do the ones at the top, right? Because they're not all being played at the same time, right? We have to make that choice. Do we play the root note, the bottom one, for the entirety of the measure? Do we play this middle one for the entirety of the measure, or do we play the 4 in sequence? We did. What did we decide? Let's do the low note. Okay. Right? We have to make a decision, so let's just make the decision and all do it the same way. Okay? Okay, so let's talk about the frequencies. Okay? The durations, okay, this actually is somewhat arbitrary. Okay? Here are the duration values, okay, that are used in that particular song. Okay, so now looking at those numbers, does that kind of make sense? Does it make sense that the dotted eighth is 384 while the eighth is 256? Because it's 1.5 times, right? Yeah? Okay, so could I have taken all of those numbers and cut them all in half? Right, so could I have made the 16th note duration 64 instead of duration 128? Okay, they're all even, so I can divide them evenly without any consequence. Okay, and that's good because I'm in my delay looping, I was iterating, and obviously you can't iterate over a half number, right? But could I have just chopped all of those in half? What would have been the consequence to the way the music would have played? It would have been at twice the tempo. Okay, meaning from the hills of Maine to the western plain or where the cotton's blowing, that's a particular tempo. If I cut all of those numbers from the hills of Maine to the western plain to where the cotton blowing, same frequencies, but I'm playing it a whole hell of a lot faster. Like chapel sing, exactly. Okay. So let's just use this same table for our durations, okay? Now, there's one thing on here that isn't relevant to us because that's the whole note. There are no whole notes in our song, and there can't be because it's in 6/8 time. And a whole note is 8/8 words of stuff. Yes? No, actually, they would be dotted half rests because you cannot have a whole note in 6/8 time, right? Because it adds up to more than 6/8. So in our case, for this particular song, we don't have any whole notes. Okay, but let's just use the durations here for the rest of them. Just keep them exactly the way they are. Okay? Good? All right, the frequencies. Let's go to Appendix E. Or we can actually look at, there is a different thing here, okay? This tells us how to do the operations there, okay? We also have 3 different kinds of waveforms. I'll let you guys look at some of those examples because you can have sine wave, sawtooth wave, and square wave, which uses pulse width modulating. And that gives it a different timbre, a different quality or color of sound. Okay, and there's a lot of other crazy stuff you can do. This chip is actually pretty advanced, okay, in envelopes and stuff. But we'll just start. Okay, so let me get down to Appendix E. And we still haven't done any machine code. No, we're going to do this one in BASIC. And then we'll start to transit, and we'll do one thing with graphics in BASIC, and then we'll start to transition to machine code. Okay, so Appendix E. Where is Appendix E? Here's the memory map, Chapter 6. Appendices, here we go. Appendix A, that's got the PETSCI, screen codes, ASCII and character codes, screen and color maps, music note values. Oh, here we are, Appendix E. Okay, so here are the values that are associated with it. So for example, if we go to the decimal here is that doesn't correspond to the hertz, I don't believe, because, yeah, okay. Anyway, the notes here, right, C0, 1, 2, and so on, is basically which octave, okay, you're in, and all the way up through, in this case, B7 is the highest note you can play, which I don't think is this many hertz. The 64 kilohertz would be way too big. Yeah, these are all the keys, right? It's in Appendix E, okay? All right, but in particular, it gives us the high and the low for each of them, right? So using this appendix and using that other table of the values and the sheet music, we can then write down for each note its high and low, okay, and its duration. Okay, so when we produce this, what order do I want to write everything down in? High, low, or low, high? Well, but the table's in high, low, so which actually makes more sense to do? It'll be easier to copy out of the table. Well, because it's listed in the table in high, low order. Right, okay. So let's actually do that. Let's use high, comma, low, comma, duration. Okay, we all have to do it the same way, obviously, so that we can read in the values collectively. But let's do it that way simply because that's the order that the table is in, and that way we don't have to reinvent the wheel. Okay? All right, so that's basically a big chunk of assignment is essentially you guys are going to have to produce a list of data statements for your page, for your voice, and then we'll have to glue everything together, okay? Now, I guess the other thing we need to decide is I will update the Canvas post because I just realized you guys will have to include line numbers, but I want obviously not to use the same line numbers because that won't work. Okay, so I'll give each of you a range of line numbers that are just for you, And that way we can combine everything without any trouble. Okay? Oh, I already did that. No, well, semi. I already did that. So, okay, let me go back to the assignment. Well, okay, so I think what I tried to do here is remember that some of you do have some musical training and some of you don't. Okay, and so I tried to split it up in such a way that you guys were somewhat distributed. Okay, so for voice, okay, which would be the vocals, is going to be Rippy, Cole, and Simon. Okay, for the treble on the piano, John, Shane, and Evan, and for the bass on the piano, Drake, Jake, and Owen. Okay, is that okay? That Owen, not the other Owen. Yeah, we have two Owens. Yeah. Yeah.
Of course you would say that.
Yeah. Okay. Then also, for the sake of the parallelizing, the pages, Rippy, Shane, and Owen on page 1, Cole, Evan, and Drake on page 2, and John, Jacob, and Jingleheimer Schmidt on page 3.
Wait, hold on. Let's wait. You want 1, 2, 3, but you split it up 1, 2, 3. So are you saying that page 1 goes to me, page 2 goes to Shane, page 3 goes to Owen, or are we just doing it as in many?
No.
Wait, no, I see what you're saying.
Yeah. Rippy, Shane, and Owen, who are all doing different voices, are all doing page 1.
I see that now.
Okay. And this way we have coverage of all 3 pages with all 3 voices. Okay. I will update this for your line number range. Okay. Because obviously we're going to need that. And that way every single person will have a different range of line numbers. And that way we won't get things screwed up. Okay. The upside down what? It doesn't matter. Yeah. So if these are towards the upper half of the thing, and so the tails go down simply because it fits better. Yeah. Yeah. So there's the convention that when you get to a certain point, you flip them upside down just so it fits better on the. Right. Okay. For this one's treble, Treble, and the other one is bass, Bass. Okay. You're in treble. Okay. So you look up treble clef, and to know which note is which. Yeah, treble clef, Clef. Okay. So this kind of makes sense. Yeah. All right. Now I suppose we haven't looked at. It is. We haven't looked at the rest of the code for the multi-voice example, but it's in the manual and it's on the D64. So why don't you guys take a peek at that before class on Thursday? The example for the multi-voice, the thing that I played. Right, just to look at how the code works there. And we'll talk about that at the beginning. Okay? All right, be gone.